Now we look at the design in general and we start with the code converter. For the design of combination circuits, first we need to state the problem, which we call problem description. From this problem description, you do everything else. Now, from the description, the first thing you do is you determine what are the inputs and what are the outputs of the circuit, which means how many inputs and how many outputs, and then you assign symbols to the inputs and outputs. So you give them names. And step number 2, you derive the truth table of the circuit. Step number 3, you derive the simplified Boolean functions. And finally, you draw the logic diagram and verify the correctness of the circuit. In our course, we deal only with Boolean functions for the description of the circuit, and we don't look at the hardware description language because this applies when the circuits are very large, which is not our case. When we look at logic minimization, we usually minimize the number of gates that we use in the design and then the number of inputs to the gate, which we call number of literals. We don't look at the propagation delay and number of interconnections and limitations of the driving capabilities, which we covered earlier. We call them fan. At the truth table to see the values of x is equal to 1 for the combinations from 1 to 4 and 9, 1 through 4 and 9, and the others are 0. So we come here, we write 1, 2, 3, 4, and 9. We put these ones, and the others 0, 0, 0, 0, 0. And of course, we have combinations 10 to 15 will be don't cares. Again, with this, we can construct the Boolean function by making loops on the Karnaugh map. So we have this loop here, and this is second loop, and this is a third loop, and we can write down x equals b prime c or b prime d or bc prime d prime. Exactly the same, we make the Karnaugh map for y, and we find that it has two loops, this one and this one, and finally Karnaugh map for z, which has only one loop, which is these 8 cells in the Karnaugh map, where z is equal to d prime and y equals cd or c prime d prime. Actually, with these two steps, truth table and minimization, we have the circuit. Now with this, we can easily draw z is equal to d prime. So this is d, we have inverter, and that's z. And then y equals cd or c prime d prime. So that's cd and c prime d prime. And this is OR gate, and this is y. And x equals b prime c or b prime d or bc prime d prime. So we write all these inputs and we say this is x, and similarly w equals, it needs two AND gates, bc and bd and a, and that is w. We can do that. So we have, in essence, 4 separate circuits. Or maybe better, in order to minimize the gates, look here how many gates do we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and an inverter. We can probably improve by using the same gate as we can see here. So we can keep z as is. Now y, which is cd plus c prime d prime, we can write it as cd plus c or d prime using De Morgan's law, of course. And x, we can write it as follows: b prime c plus b prime d. We take b prime parentheses c plus d close parentheses plus b, and c prime d prime, we write it c or d prime. And finally, we write w as a plus b and parentheses c plus d. So this c plus d, this OR gate, we use it once here and once here and once here with complement with inverter and once here. So we use the same OR gate 4 times. This is how the circuit will look like now. W equals A, so that's A, or B, that's B, and C or D. So this is C or D. We brought it from this OR gate that we have just mentioned. So that's W. Same thing for X is equal to B prime. So this is B prime here, and C or D. Again, this is C or D. Or the other side, B, that's B, and C or D prime, which is this quantity, X, and Y equals CD here, or C or D prime, and Z equals. So with this, we save actually in the number of gates.